All right. Thanks, Paul. It's really nice to give a talk in this series. It's not the typical thing that I would normally talk about, unless I was teaching, of course. And so, yeah, it's a bit of a challenge, but I'm happy to take it on. You guys, please be sure to interrupt and say something if I before I make a goose of myself and then say wrong things. Because I feel like, I don't know, I feel like I'm almost like a student presenting to my teachers because a lot of you guys have done things on ancient solutions and I'm just an interested observer really, but I'm trying to learn. Okay, so the plan for my talks, and I don't know how many there will be, we're just going to have to play it by ear, I guess, but the plan is not very, it's not very difficult to understand. We're going to do the Euclidean case of the result, and then we'll see that basically everything carries over to the manifold setting. Not really, but at least for the first theorem, that's true. Okay. And my idea is that I'm going to try to give details where I can, but not get bogged down too much. Okay, so first some context. We're talking about the heat equation. So let me write it down. ddt of an unknown function u equals the Laplacian of u. And here we're in Rn, okay? And we're interested in specifically in ancient solutions, like it says up here. So for example, if we take the function e to the x plus t, then we can calculate its time derivative in 1D. Okay, so this is for n equals 1. And we get, and this is, I'm really taxing myself doing this calculation, x plus t. And that's equal to dx e to the x plus t. And of course, this is a very nice function, and it's an ancient solution. It's an ancient solution. In 1D. And we can see that it has exponential growth. Of course, it is an exponential, okay? So it has exponential growth in space and in time. Okay, and now we might ask ourselves questions about how many ancient solutions can there be of the heat equation, and what properties could they have? And many people have asked themselves this question, and I just want to mention one thing, I guess, which is Lin and Zhang, and this is Yao's Liouville theorem. And what does it say? I'm not going to give like a full statement, but I'll just give a short summary. It says that if U is non-negative, okay, and it's ancient, and it has growth slower than or less than, depends how you think about things, e to a constant times distance to some fixed point, doesn't matter where it is, plus, and then in the time you need to take a square root because of the scaling of the equation, So if you have such a thing, then it is constant. U is constant. Okay, and we can see by my very taxing example that this is sharp. Okay. So this is a nice result, and it's in a way not that surprising because, well, it was conjectured before, but also in analogy with the Liouville theorem, it's not too surprising. Okay. But it does lead into our kind of natural question, which is what are the non-negative, let's call them positive, ancient solutions? In particular, we're going to first investigate a representation formula for these kinds of solutions. And then we're going to discover that we can say a lot more about the structure. Okay, I don't want to survey any more literature than that. I should say that pretty much everything, none of this is my own work. So let me just be very clear about it. So I'm not sure what to write, but most of this is from Lin and Zhang's paper, which was on the archive in 2017. I'm not sure what year it was published, but yeah, just to be clear, this is not my own work. Okay, but it is great. Okay, so the first theorem. Theorem 1. It goes like this. It's a representation formula. So maybe I'll just write this here. Okay, what does it look like? It goes like this. So we let U be a non-negative, and this is, of course, in Euclidean space, solution to the heat equation. And it should be ancient, and so I'll just say it like this, Rn cross minus infinity, and we'll go up to 0. Okay, and then the first kind of main point, which is actually very easy to see, is that if you make the function composition by reversing the time variable, you get what's called a completely monotone function, and these have a very nice integral representation, which is due to Bernstein. So I'll talk more about that in a second. Is a completely monotone function. So this idea completely monotone is jargon, and I'll define it in a second. Completely monotone function in T. Okay, and so what does this mean? It means that eventually, after quite a bit of work, well, I think it's work, it's many steps. So furthermore, there exists a family of non-negative Borel measures we'll call them mu, and they're parameterized by an S. These are measures on the unit sphere and a Borel measure in time. Which we call rho, and it's going to be supported on 0 infinity, such that, okay, now we have our fancy, wonderful formula. U of x and t is integral, and then we have this representation. Square root s d mu. Okay, now variable is psi, and the other one is s. And then, if you're wondering why I'm not writing in this column, it's because I've got the Zoom interface on top of it. D rho s. Okay, maybe I can minimize it. Can I minimize myself? Oh, okay. All right, that's the main thing. So let's do a box around it because I can. There we go. Isn't that wonderful? Messy handwriting aside, that is just a beautiful formula. Maybe a remark about this. When I don't want to spend too long making remarks because then I'll never get to the proof. But if you're interested in these kinds of representations, then you might want to look up Witter's work. He wrote a book. He's written a few books, but one book has the result from '63 where he showed that if you have U, a positive ancient solution in Rn. So, okay, this is getting it. It's anyway, that's just the notation. Then U of x and t is, okay, so this is a version where you're integrating over Rn instead of this polar expression. E x dot y plus t y squared, and then it should be d mu of y. And here mu is a non-negative Borel measure. So with all the measures floating around, you can guess there's going to be some measure theory here, but I'm going to try not to focus on it. Okay. Yeah, so that's the first theorem, representation formula. And, okay, and that's what I'm going to talk about proving, or I'm going to try to prove it actually. But somehow it's not the most, I mean, I love it, but maybe it's more like, it's not so impactful in its statement. The second one, though, is a doozy. So this is, let's just call it a structural theorem, whatever you want to call it. Okay, it goes like this. Okay, wait. So we let HQ, I don't like this notation, sorry guys, but I don't like this notation, but I'm doing it anyway. Rn cross minus infinity 0. Wherever I see a h with an exponent, I think Sobolev space, but anyway. And here, by the way, maybe I'll make a few little things. Q should be bigger or equal 1. Okay, this is going to denote space of ancient solutions. To the heat equation that satisfy this growth condition. Oh, right. So maybe I didn't even make the remark back here, but you can see that in this theorem, U is a non-negative solution to the heat equation. It's a non-negative ancient solution and no growth condition, right? So this is pretty much generically true, which is amazing. Okay. All right, so now we're assuming some condition. We assume something like what we had before. We need to take a reference point, and this D denotes distance. Okay, we have square root of t plus 1 to the power q. This should be true for all x and t. Okay, so that's the space HQ. All right. And there's two conclusions here. Well, there's one big conclusion, I suppose. There exists a C and an eta. Now, yeah, okay, I'll say more about what this eta is in a second, such that the dimension of the space HQ Rn cross minus infinity 0. I should just call it HQ, but it really looks like a Sobolev space, is bounded by CQ to the eta plus 1. Okay, so this really tightly controls how many non-negative, how many ancient solutions you can have. Not non-negative, how many ancient solutions you can have. Okay, this eta, by the way, here, if you're wondering what it is, it's the log. There's a chat. Eta is not exactly n minus 1, but it's, yeah, I'm going to write down log base 2 of the doubling constant. And so eta is called doubling dimension. Yeah, so maybe in Euclidean space it's n minus 1. D0 is the doubling dimension. So what is the doubling dimension anyway? So that's the estimate on sort of the number of balls you need to cover a ball of half the radius with balls of some given radius. It's linear, I think it is anyway. It's linear in dimension, and the coefficient of the linear term is less than or equal to 10. Anyway, if people are interested in what this thing is, then I can work it out. Do we have more chats? Ben wants to chat? No. Happy for anyone to chat at any time. Okay. All right. Now, even more remarkably than this is already pretty cool. We have this decomposition, furthermore, for k equals the ceiling of, why do I always write Christoffel symbol? They just haunt me, Christoffel symbols. Ceiling of q over 2. U of x and t equals u0 of x plus u1 of x multiplied by t, and so on. You get a whole bunch of these guys. T to the k minus 2 plus u k minus 1 x t to the k minus 1. Okay, and this expansion is amazing. So these coefficients satisfy this kind of PDE. The Laplacian of ui is I plus 1 times ui plus 1. And then you might ask, well, what happens for the last guy? Well, he's harmonic. And the Laplacian of u k minus 1 is 0. It's harmonic. Isn't that beautiful? It's a wonderful theorem. Okay. Remark. Okay, this is not really a very deep remark, but if the Laplacian of uk minus 1 is 0, then the Laplacian of uk minus 2, okay, is k minus 1 Laplacian of uk minus 1. oops, sorry, Laplace squared. That's what I meant to say. And that's 0. Okay, and then the Laplace cubed of uk minus 3 similarly is also 0, and so on. So even though they're more special than that, this is really the defining relationship here, but there is a stratification, or at least I think about it like this, where this is harmonic and this one is biharmonic, and then etc. etc. So I find that interesting. There's an analogy here with spectral decompositions of various things, including submanifold immersions of submanifolds. But anyway, I'm not going to go into it. I do find it interesting though. Okay, so what we're going to do is talk about proof of theorem 1. And I'm going to need a few things. So I've broken it down into 10 steps, 10 easy steps. It's a 10-step program, 10 steps. I don't think 10 is the normal number, but anyway. The first step is going to be called monotonicity. And this is going to involve application of the Lie-Yao differential Harnack inequality. Right, I'll say more about that. The second one I'm going to call Bernstein. And that's going to be when we use the completely monotone property for all derivatives, time derivatives of the, what you prove using Lie-Yao is that when you have an ancient solution, you get a positivity or non-negativity of the time derivative, repeated time derivatives of the solution. It comes straight out of it. And then you do a change of variable to make that alternating in the time derivative by making t to minus t. Anyway, and then you get completely monotone. But I'll say more about that in a second. The third one is, well, it wouldn't be a proof without Fabini's theorem. So, and then we do inverse Laplace. And then maybe I'll go up here. The next one is an integral estimate. And at this point, we're definitely in the realm of measures. There's going to be measures everywhere. So get your, if we're Dora the Explorer, then you can get your, there's a measure. I see a measure over there. Hats on. We're going to derive PDEs for various functions. One of them is going to be called H. And that's going to be important. And then we're going to use a Harnack inequality for measures to get certain estimate. Go away notification. Then we're going to use Radon-Nikodym because it wouldn't be a proof with measures without it. And then we're finally going to get a PDE for this Radon-Nikodym derivative of the measure that we care about, which is going to be d nu at x with respect to d nu at 0. And then last step, step 10, is we're going to apply a representation formula, which, as far as I can tell, is due to Caffarelli and Lippmann, but there are some other references that have, I think, the same kind of formula from earlier. But yeah, so we're going to apply a representation formula for this measure, and then plug it all, mix it all together, and we'll be done, and that'll be great, and we'll be happy. Okay. So I don't know if I'll get through all of it today. I don't think so. But we're going to see. Hopefully, I'll hit a good balance between giving enough detail to have a decent idea of what's going on and not spending too much time. So big theorems that I'm not going to prove, or I don't plan on proving, is Bernstein's theorem on completely monotone functions, but I'll at least state the formula. And the Caffarelli-Littman representation formula, I don't plan on going through that. For Li Yao, I'm going to give an idea of the proof, but I think that everyone here can prove it better than I can anyway. So this is really just for the benefit of people who maybe are just learning. Okay, so here we go. Okay, so we're going to need the Li Yao theorem. And it goes like this. You let U be a positive solution to the heat equation in, and I'm going to use the local version. Yeah, I'll say more about that in a second. So we take a space-time cylinder, QRT, which is going to be the ball of radius r at x cross t minus big T to big T, like that. All right, and then the estimate, which is like a differential Harnack, or is a differential Harnack, has this form: grad u squared over u squared minus ut over u is bounded by some constant, and then you have the localization effects and the time, and this should be in a sub-cylinder of this one. So let's take q r over 2 t over 2. Okay. Here, no, I sort of wrote it, but where Cn is a constant depending only on n. Okay. All right. So I don't want to prove the full statement that I've just given. What I'd like to do is talk about the version that does not involve the localization. Okay. So because I think the proof that, I don't think this is not the Li Yao proof. But anyway, if you want the full proof, you can definitely look in Li Yao. And I'm sure there are many good proofs of it, but anyway, this is one proof. Okay, so let's first make a definition. Right, you can look at this equation and you can see that sort of ut over u is the time derivative of log u, and this term, grad u squared over u squared, is the square of the gradient of log u. So let's set a function f to be the logarithm of u. And that's well defined because u is positive and smooth as we like. Okay. And then we should probably work out equations and relations that f satisfies. And I think this is very similar to what Ben did, but he did the elliptic version. Okay, so we got this one. And we've got Laplacian of f. Okay, so what's that going to be? You're going to take the divergence of grad u over u, and so you're going to get the good old product rule, which looks like this. Okay, so you get the trace over this expression like that. Okay, and then of course we can work out what kind of PDE f satisfies, which comes to no surprise for anyone. It's this. Okay, because this term here is just the gradient of f squared, like we talked about a second ago. All right. Not much has happened. And now I'm going to do something. So I'm going to rewrite that equation. Sorry, my thing just bugged out for a second. Okay, ddt f equals Laplace f plus gradient f squared. And now I'm going to do something dramatic, and I'm going to take the Laplacian of both sides. So the ddt of the Laplacian of f is Laplace f, and then you have this Laplacian of gradient f squared. And I think you guys can see that I was drawn to this proof because of all the derivatives. You know, I can't stay away from multiple derivatives. So what is this thing? This is div of 2 grad f dot f, grad f, like that, which is Laplace f. And then we've got, okay, so we're going to get a term which is like the Hessian. And then we're going to get a term which is the gradient of Laplace f in the direction of gradient f, okay, which is actually just a beautiful expression. It really is good. Maybe I'm not doing it justice, but this is just a nice PDE for Laplace f. So what is it? ddt minus 2, and our first order term is this guy. And our Laplacian is just perfect. Okay, so we got like that. And then that is just this Hessian guy here. And the only fly in the soup, bug in the soup for this one is that this is not Laplace f squared, but it's almost Laplace f squared. So if anyone needs a proof of this, I'm happy to do it, but I think everyone can do it. This is just a simple algebraic inequality, but you can control the Laplacian of f from above by the Hessian, and you need to pay the price of n, where n is the number of, well, number of eigenvalues. It's the number of terms. It's the number of dimensions. So, okay, so what do we get? So we get ddt minus 2 times the gradient in the direction of grad f, Laplacian Laplace f is greater than or equal to 2 over n plus f squared. Whatever. Okay, that's fine. All right. But now there's another function that satisfies a very similar equation, which is this guy. So we're going to write it down as well. ddt minus 2 times, this is a little bit sneaky because the function's not going to involve the space variables. So all of this is just going to be 0. But we take n over 2 times t minus t. And what is that equal to? Well, if you differentiate it, it's 2 over n times n squared over 4 times t minus t squared. Okay, and now of course this thing here is just the square of this again, right? It's exactly the same form as this equation here. And so what that means is ddt minus 2 gradient f minus Laplace. And then we just mix these guys together like this. It's greater or equal 0. And it's just a short hop and a skip to the maximum principle, and we get preservation. If we had it at all, we get preservation of the inequality Laplace f bigger or equal minus n over 2 times t minus t. And if you think about it, of course, we must have had this inequality. We must have had this inequality at some time because the estimates that we have for ancient solutions. So that means that that we must have this for time sufficiently negative, so we have it for all t. And if you use our little equation we have for f, what's our equation for f? It's up here. So that, if we rearrange it, we get the plus f is d dt of f minus gradient f squared. That means that d dt of f minus gradient f squared is bigger or equal minus n to t minus t, like that. But of course, f was log u, and so we get the statement. Well, it's not really the statement because I didn't localize it, but you can localize it. Of course, you can localize it. Okay, so just so I can check that I'm not telling fibs, let's just have a little look here. We've got a plus sign on the ddt of u and a minus sign on the n. Oh, why isn't it scrolling up? Here it goes. Yeah, and that's right. Okay, so I think it's okay. Yeah. All right, so for the full result, localize. Okay. Alrighty. So no questions, then I will keep going. I'm just gonna keep talking into the void. Alrighty, so step one. This is the monotonicity step. Oh, there's a chat. Okay, thank you, Julie. All right. Yeah, I know you guys probably seen that derivation of Liao 1,000 times. For u greater equals 0 solution to the heat equation, an ancient solution, I'm just writing the same thing over and over again. We apply Liao, and what do we get? Yeah, we get, well, we don't need a half here. I just hesitate before I write a half because you can put anything here that's less than 1, but anyway, it doesn't matter. It really doesn't matter. We're going to throw this term away, but I don't know. The struggling mathematician in me doesn't like writing that down, but anyway. So this half can be anything less than 1, but we're going to throw it away anyway. We don't care. Okay, so this is what we just had a second ago. All right. So what does this mean? This means that ut at x and t is going to be bigger than, we throw this term away, minus c n u x and t times 1 over r squared plus 1 over t. But now you see what we can do. This u of x and t is just a number, so it's bounded in particular, and we can take r and t as large as we like. So what this actually is saying is that ut is greater than or equal to minus epsilon for all epsilon greater than 0. And as we teach our baby analysis students, this means the only way this can be true is if ut is actually greater than or equal to 0. And that's step 1. Isn't that easy? Easy step 1. All right. Step 2. This one is Bernstein. Okay, so since we showed that ut is greater than or equal to 0, if you think about the hypotheses that we used, we can actually take our PDE, which is the heat equation, differentiate that in time, and apply the same argument to UT, which will show that UTT is greater than or equal to 0. And we can keep going forever. And so we actually just get that all the time derivatives of U are non-negative. Okay. All right. And so then what we do, and I I realize that we've yeah, okay. Then we note that therefore, if we differentiate k times u, but we replace t by minus t, like that, and then we multiply this. I'm going to move this across a bit. And then we multiply this. How do I turn that off? Go away. Is it going to work? Okay. Go away. Can I put my pen back? Okay, thank you. Multiply this by minus 1 to the k. We're going to get that's greater than or equal to 0. And so what this means, this is the definition of this function inside here being completely monotone. Okay, so the mapping that goes from xt to u of x and minus t is, that's just the definition, a completely monotone for each fixed x, right? It's important to keep in mind that this is just for a fixed x. So for each x you do this, and that's kind of the only sort of technical wrinkle in this proof, at least as far as I can tell. It's completely monotone function in t. So what does it mean? It means that Bernstein's theorem applies, and Bernstein's theorem tells us that okay, so we make the definition, this is going to be called f x of t, and we're going to have fx of t is going to be oh no, sorry, scratch that. It's not fx of t. Oh, yes it is. Sorry. I confused myself. So fxt, which is that function, sorry, ux minus t, has this expression which looks like a Laplace transform. Okay. Except you have a measure here. So this is Bernstein. I knew I'd managed to confuse myself at some point, where nu here, now this is also for each fixed x, is a non-negative Borel measure on 0 infinity. Okay. And that's Bernstein's theorem. Are there any questions? I guess not. So we're just going to note down an alternative expression, which looks like this: fx of t equals fx of 0. Okay, and this, by the way, is just u of x and 0 plus, and then integral 0 infinity e to the minus ts. Okay, but then because we put this fx0 here, we just subtract 1, and we get d nu s and x. Okay, so we're just going to use that in a second. The next step. Just going to be step 3, which is great. Why? Thank you. All right. So the next step is very creatively called Fabini, because we're going to use Fabini's theorem. Okay. So we calculate fx t. Right, now just remember that this is u of x and minus t. Okay, so the formula that I just wrote down has fx0, which is u of x and 0. Okay, so this is actually just the formula I wrote down a second ago. I'm just going to write it again because I like to see things all on one page. All right, d nu s of x. Okay, and all right, so now what do I want to do here? I want to bring this u of x and 0 into a single integral, and then I'm going to call the part of the integrand a new function. Okay, so let's see how we're going to get this to work. All right, so first I want to integrate minus t. Okay, and I'm going to look at this term as the integral from 0 to s of e to the minus t, and I need to introduce a lambda, d lambda, d nu. Right? So this is just integration. Okay, and now I'm going to swap these measures using Fabini. And you know, when you're teaching, you always need to draw a triangle, but in this is a pretty regular case, and so the outer limit is 0 to infinity, and then here we're just going to get lambda to infinity, and we just collect these terms together. I've put the minus at the front, t e to the t lambda, integral lambda to infinity, and then we've got, okay, we've swapped the measures, just like that. That's Fabini. That's the Fabini step. Okay, that's a B. All right. Okay. Now we also need to note that the integral, so this t e to the t lambda minus, guys, you're supposed to tell me when I make silly typos. So the integral of from 0 to infinity, this is sort of on the back of a napkin, of t e to the minus t lambda, d lambda. I know this is a hard integral, but trust me, you can integrate it, and you get 1. All right, so it's pretty good. In particular, you can think of this function u at x and 0, just a number. You can multiply it by 1, right? And you can multiply it by this integral. And so you get integral. That's how you bring it in, right? You just note that this has measure 1, t e to the minus t lambda, and then u of x and 0 minus the integral from lambda to infinity of d nu at s and x, like this, d lambda. Okay, and yeah, okay, we don't like that lambda variable. We're going to call it s from now on, and we're going to call this thing inside here a function h. And if you remember the little steps that I said, one of them was deriving a PDE for h, and this is the h. Okay, and we just changed variable, just the name. Okay. All right, All right. So what can we say about H? We can, well, let's just write down the formula for it because, you know, why not? Oh, I still have a lambda. What did I do? Oh, thank you, Julie. Thank you, Julie. Okay, h of x and s is equal to this expression in S, but if you remember the integral representation from Bernstein for u, then you can combine these integrals together and you get the integral from 0 to lambda. Oh, I've got a lambda again. Cancel. Lambda, stop harassing me. All right. 0 to s, and then here I want d nu sx. Okay. So that's true. And what can we say? We can say h is continuous. So if we fix an x and we think about it as a function of one variable, is continuous from the right. So you can say right continuous. It's non-decreasing because the Borel measure is non-negative. And yeah, that's all I want to say. Okay, so what this looks like to me is something like a Laplace transformation. So what we can do is apply an inverse Laplace transformation, so long as we have some nice properties of H, which we do. Okay. So this is step 4. Inverse Laplace. All right. Okay, so it's getting to 4 o'clock. Maybe what I'll do is leave this one here and see if there are any questions. And yeah, because I've got to unfortunately buzz off at 4 o'clock.